Hello PreCalc, here we are with 10.7 polar coordinates. Alright, going to expand your brain a little bit today, working with something that you probably have not worked with before. We have been representing graphs of equations as collections of points as x comma y on the rectangular coordinate system, where x and y will represent directed distances from the coordinate axes to the point x, y. In this section, we will study a different system called polar coordinate system. To form the polar coordinate system in the plane, fix a point O, called the pole. It's going to be at what you would normally call the origin, and construct from O an initial ray called the polar axis as shown below. Then each point P in the plane can be assigned polar coordinates r, theta, as follows. R is your directed distance from O to point P, how far out from the origin or pole it is. That's what it says R is, and I kind of think of R as a radius, so that might be helpful for you. And theta is our directed angle, measured counterclockwise from the polar axis, aka the positive x-axis, to where our segment would be. Okay, to get us started here, we're going to start with plotting some points to kind of get used to our polar grid. Okay. First off, we have 3, negative pi over 3. Okay, so our length out is going to be 3 units, and our rotation is going to be negative pi over 3. So we're starting here, we're out 3 units, 1, 2, 3, and we're rotating down pi over 3, which is going to put us at 5 pi over 3. So here's our line that we're on, our rotation line that we're on, 5 pi over 3, and 1, 2, 3 units out, 3 rings out. We'll call that one point A. All right, point B, our directed distance is 2, our rotation is pi over 6. Okay, so we're pi over 6 up and 2 units out, and there's going to be point B. We're changing this one to 5. If we keep having all these 2s, then we're going to overlap, and it's going to get kind of crowded in there. Let's change that to 5. 5, negative pi over 6. So we're going to go pi over 6 down for our rotation, and 5 out. 1, 2, 3, 4, 5. That's point C. Only labeling these basically because we have so many on the same grid. Ooh, a negative R. Okay. So rotating 2 pi over 3 over here. Okay, we're thinking we're going out this way, but a negative is actually going to push us the opposite way down the 5 pi over 3 line, 2 units. 1, 2. So we rotated 2 pi over 3, and if we had a positive R, we'd go out along that way, but we have a negative R, which is going to push us down this way. And B is going to be right there. Or D, excuse me. And E, let's change this to a negative 5. Okay, so negative 3 pi over 4, so we're rotating down this way. 1 pi over 4, 2 pi over 4, negative 3 pi over 4. And then we have an R value of negative 5. So instead of coming out this way, we're going to go backwards this way. And here's where we're going to be. So we went negative rotation, negative 1 pi over 4, negative 2 pi over 4, negative 3 pi over 4. If we would have had a positive R, we'd be coming out along this line. We had a negative 5, so we're actually going to go backwards 5. And out along the pi over 4 line. And that was our last point, E. Okay, so as you could probably guess, from a couple of those points there at the end, especially with the negative r's, there's definitely more than one way to get to a point. In the rectangular coordinate system, each point has a unique representation. This is not true for polar. For instance, the polar coordinates r, comma theta and r, comma theta plus 2 pi would represent the same point. Okay, you just keep spinning multiple circles, more than once around the loop. Another way to obtain multiple representations of a point is to use negative values of r that we saw there, because it flips it back. Because r is a directed distance, so it flips it backwards. R comma theta would be the same as if you go another pi or half circle around and then have a negative r, so it comes backwards at it. Okay, in general, the point r comma theta can be represented as r comma theta plus 2 pi n, or negative r plus or minus 2n plus 1, so you're going to get odd multiples of pi, where n is any integer. Okay, so how can we get multiple representations of, let's change this, it's just nicer having a larger r value. You have these smaller ones and it gets kind of crowded in there. I think I changed this to 4 in class earlier. 4 comma 3 pi over 4. So rotating 3 pi over 4, positive direction. 4 rings out. 1, 2, 3, 4. How else could I get to that point? Keeping theta between negative 2 pi and 2 pi. So obviously you could keep adding 2 pi. Let's not do that. Let's think more than that. Okay? Well, we just spun this way. We could spin this way. So we could have a positive r value with a negative rotation. We could rotate negative 5 pi over 4 and then still go out 4. Okay, so we still have a positive r but a negative rotation. And now we're going to have negative r's. Okay, so if I have a negative r, that means I want to be over here at 7 pi over 4, and then my negative r flips to this side. Okay, so we could have positive rotation of 7 pi over 4 with a negative r length. Negative 4, comma, positive 7 pi over 4, right? So rotate 7 pi over 4, and then have a negative 4 for your r, so it's going to go backwards, 1, 2, 3, 4. And we could also have a negative 4 with a negative pi over 4. So negative pi over 4 for the rotation, we rotate down pi over 4, and then we have a negative r value, so it's going backwards 4, 1, 2, 3, 4. And we'd still get to that same spot. So there are 4 total, 3 other representations for that point. Lots of different ways to get there. To establish the relationship between polar and rectangular coordinates, let the polar axis coincide with the positive x-axis, and the pole with the origin is shown here. X comma y lies on a circle of radius r, so it would make sense that we could do x squared plus y squared equals r squared, turn it into a right triangle. And now look at this right triangle, we can do some right triangle trigonometry. Tangent of theta would equal y coordinate over x coordinate. Cosine of theta would equal our x over the r. And sine would equal opposite our y over the r. So we can use those, and also this one, the a squared plus b squared equals c squared, to convert back and forth from polar to rectangular and rectangular to polar. And here they are again, things that will help us. Specifically, going from polar to rectangular, x equals r cosine theta, y equals r sine theta. Going from rectangular to polar, we can get our angle, our theta, from doing tan inverse of y over x. Theta would equal tan inverse of y over x. And then our r would equal the square root of x squared plus y squared. Convert each point into its rectangular coordinates. Okay, so this is in polar. This is my r. This is my theta. Okay, so our x would equal r times cosine of theta, and our y would equal r times sine of theta. So we have 2 times cosine of pi and 2 times sine of pi. Okay, let's think about pi. Where's that at? Pi. Okay, negative 1 comma 0. So cosine should be negative 1. And sine should be 0. So negative 2 comma 0 is our rectangular coordinate. Okay, in the interest of time, we're just going to throw the answer one up there to B. Okay, same stuff, our cosine theta, our sine theta, pi over 6. On the unit circle would be radical 3 over 2 comma a half. So we have, and our r value was radical 3. So radical 3 times radical 3 over 2 would be regular 3 over 2 now. And then our sine, radical 3 times a half, will be radical 3 over 2 for the y coordinate. 3 over 2 comma radical 3 over 2. And you can pause that and look at that some more there if you need to. Converting our rectangular points to polar. Converting rectangular points into polar. All right. So we're going to have r squared equals x squared plus y squared to get our r value. R squared equals 2 squared plus 2 squared. 4 plus 4 should be 8. So we're going to get radical 8, which would be 2 radical 2. Okay, our theta would be tan inverse of y value over x value, 2 over 2. Hopefully you don't need that calculator. 2 over 2, we're looking at 45 degrees, or pi over 4. So our polar coordinates would be 2 radical 2 comma 45 degrees, or 2 radical 2 comma pi over 4. All right, if you wanted to use this one over here, you can go ahead and give that one a shot. Push pause. Okay, and this is what I have for that one. All right, hopefully we can just plot this point and kind of tell, all right, that my unit is, my r value, I'm 1 unit out from the center, and my rotation would have been pi, so we're looking at 1 comma pi. Otherwise, you can go through all the formulas there and still come up with 1 comma pi. While we have the answer key here, okay, equation conversion, to convert rectangular equations to polar, you just need to replace the x with r cosine and the y's with r sines. For instance, the rectangular equation y equals x squared parabola can be written in polar form as follows. Okay, replace the y with r sine, replace the x with r cosine squared. Okay, and then it gets you r equals secant times tangent. That was the equation in polar form for a parabola. That's a big jump from here to here. Okay, so they squared the r and the cosine, r squared cosine squared. Divide both sides by r. Sine equals r times cosine squared. Now we're going to divide by cosine squared. So we have r by itself. Split the cosine squared up into sine over cosine times 1 over cosine. And there's where your secant and tangent come from. On the other hand, converting a polar equation to rectangular requires a little bit more ingenuity. You got to think about it a little bit. Example 5 demonstrates several polar to rectangular conversions that enable you to sketch the graphs of some polar equations. Okay? Describe the graph of each polar equation and find the corresponding rectangular. R equals 2. So if you just have a radius and don't have any restrictions here on your theta, it's just going to give you a circle. We can use r squared. If we square both sides, we get r squared equals 4. And now I can use my r squared substitution. R squared equaled x squared plus y squared on the other side. And we can see now we have a rectangular form there for a circle. Theta equals pi over 3. This is a tough one. Okay, I'm trying to get this into rectangular. I need an x and a y. I don't have like an r squared that I can substitute in. But what had x and y as far as trig functions? Tangent. So if I do tangent of both sides, okay, tangent theta was y over x. Tangent of pi over 3 is radical 3. Multiply the x up. And now we have the equation of a line with slope radical 3. R equals secant theta. This one's kind of crazy. Think about what secant is. 1 over cosine. Okay? R cosine was x. So let me multiply cosine to both sides. So we have r times cosine theta equals 1. R cosine theta, we had a substitution for that. That was x. We get x equals 1. It's a vertical line. Wow. Would never have guessed that from looking at r equals secant theta. All right, so there you go, folks. Take a look at that. Let me know if you have any questions. Try some of these problems out. Okay? It's important to try these problems out in the early stages here so we don't get shocked, I guess, by the progressions here as things get more difficult.